Steam billows from the towering stacks of the Ninghai power plant in China. At first glance, it seems everything is running as expected. Massive turbines churn and thrum with the heavy pulse of energy generation. Visible from miles away, this behemoth of steel and concrete stands as a testament to modern engineering. Yet, despite its size and capabilities, something surprising operates hidden within its walls. These colossal engines are never tasked to operate at full capacity. It is a mystery that begs the question, why do some of the world's most advanced coal power plants never push the limits of their design? To comprehend this anomaly, we need to delve deeper into the realm of ultra-supercritical coal boilers. While it would be reasonable to assume that, equipped with cutting-edge technology, these plants would run their enormous turbines to maximum output, the reality is far more complex. The intricate relationship between pressure, temperature, and material fatigue reveals critical engineering challenges. To illustrate, let's explore how these systems function. Ultra-supercritical boilers, like those found at Ninghai, operate at staggering temperatures exceeding 600 degrees Celsius and pressures of 27 megapascals. This creates a potent steam that drives turbines with remarkable efficiency. But therein lies the catch. The heat and pressure necessary for such efficiency also lead to a phenomenon known as metallurgical creep in turbine blades. At elevated temperatures sustained over time, metals can deform under stress, leading to structural failure. In essence, while these machines possess extraordinary capabilities on paper, the uncomfortable truth is that they must adhere to limitations to ensure operational integrity over time. Take, for example, the celebrated Siemens SST 9000 series of steam turbines, utilized in various coal plants around the globe. These turbines are engineered to withstand extreme temperatures and pressures, yet the creators have established a hard ceiling on output below their theoretical maximum. Running the SST 9000 at full capacity could accelerate wear and lead to mechanical failure due to fatigue in the high-stress zones of the turbine blades. This is not a matter of preference, it's a fundamental limitation based on physics. Consider a kettle used for boiling water. When you raise its temperature too high, the steam pressure tries to exceed the safe limits of the kettle's material. If the pressure were to climb past its design specifications, the kettle could become a dangerous projectile. In a similar way, exceeding operational limits in a power plant could lead to catastrophic mechanical events. Additionally, engineers must contend with the fact that turbine performance diminishes beyond optimal output due to efficiency losses. High temperatures and high pressures allow coal plants to operate at efficiency levels as high as 42%. This is impressive, especially when considering that traditional subcritical plants normally achieve about 35% efficiency. Yet operating at these high efficiencies forever introduces more challenges than just turbine stress. The increased thermal expansion and contraction of the turbine components also plays a critical role. As these metals heat and cool during operation, they expand and contract, leading to fatigue at an accelerated rate. Here's a moment to engage your curiosity. How often have you considered the fine line that these advanced systems tread? Is it surprising to learn that the machines we rely on daily have limitations built into their very design? Returning to Ninghai, while it produces an impressive capacity of roughly 1,040 megawatts, this figure is calculated based on a reliable and sustainable operational benchmark rather than a peak performance value. Engineers strategically cap output to balance performance and longevity. Under optimal running conditions, the plant maintains resilience against degradation, ensuring that the turbines remain operable for over 15 years, which is a substantial lifespan considering the intense conditions they face. It is easy to fall into the assumption that more output equates to greater efficiency or productivity. However, the reality shows that exceeding operational thresholds can lead to premature replacements and costly downtimes. This investment in materials and engineering to safeguard against such failures is a testament to the careful calculations involved in modern energy production. One commonly held belief is that maximizing output is the only aim of a power plant. This misconception can lead to broader questions about energy strategies and reliability. Conversely, engineers emphasize the engineering approach of prioritizing sustainability and longevity. By operating below the mechanism's maximum output, they ensure a lower risk profile for maintenance while also simplifying operational issues. Ultimately, the real trick lies in the balance between pushing ahead and knowing when to draw back. The interplay of extreme conditions challenges the materials used in these systems. The careful selection of materials suitable for high temperatures, such as the high-performance alloys developed to withstand these conditions, addresses the risk of metallurgical creep. By choosing materials that stand up to the task while remaining within safe operational limits, power plants can maintain a reliable output over many years. As we take a step back, it becomes clear that the innovation of what we see as powerful machines is supported by even more profound engineering truths about materials science and energy transformation. The modern coal power plant exemplifies a dance of science, where each step is finely choreographed, each decision weighed with consequences that span operational efficiency, safety, and the longevity of technology. At this scale, every fraction of a percentage point in efficiency lost can translate to substantial economic implications across the energy sector, highlighting the real-world stakes. Every choice made within these power plants, regarding how much they generate, the temperatures they endure, and the pressures they operate under, presents its own array of questions, decisions, and unforeseen consequences. In closing, we have explored a world where the giants of energy generation abide by principles that transform them from mere machines into remarkable feats of engineering. As we reflect on the ingenuity behind these systems, it is essential to recognize the unseen complexities and delicate balances that enable their operation. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. To further understand the limitations faced by these colossal power plants, we must delve deeper into the specifics of the materials and design choices engineers must consider. Metallurgical creep occurs when metal components are subjected to high temperatures and pressures for extended periods, leading to gradual deformation. In the case of steam turbines, this can be especially detrimental. For example, in the Siemens SST 9000 series, turbine blades are designed with advanced alloys engineered to withstand extreme conditions. However, engineers have found that exceeding a temperature of 600 degrees Celsius can induce creep distortions, which can begin to compromise blade integrity. When designing the turbine, the materials are meticulously analyzed to discover the precise temperature limits that should not be crossed. On average, each blade can sustain operation at roughly 600 degrees Celsius for about 20,000 hours before significant creep begins to occur. Looking into historical failures illuminates the consequences of pushing machinery too far. In 2007, the Lamont power plant in Illinois experienced a catastrophic failure when operational temperatures reached levels above safe limits. A structural failure of the turbine resulted in a fire that not only devastated the turbine itself but also led to extensive operational downtime, causing significant economic losses. This disaster highlighted the vulnerabilities and limitations established by engineers to maintain safe operations while maximizing efficiency. The estimations indicated that pushing for just a 5% increase in output could lead to $40 million in repair costs and lost productivity. Moreover, the phenomenon of thermal cycling, where machinery goes through frequent heating and cooling processes, drastically affects the wear and lifespan of turbine materials. In fact, on average, power plants operate with load variation of about 30% during a typical day. High-temperature materials face fatigue due to repeated expansion and contraction. Every cycle contributes to microscopic cracks forming within the turbine blades. Engineers have found that managing this thermal cycling, with careful monitoring and maintenance, has become integral to maintaining power plant functionality. Consider the thermal expansion of materials more broadly. When hot tubes within the ultra-supercritical boiler of the Ninghai power plant expand, they must effectively manage the additional strain generated upon cooling. The differences in thermal expansion coefficients among various alloys can create stress points leading to further risks of material failure. Engineers must select alloys that can endure these fluctuations. Typically, they turn to alloys like Inconel and Haynes 230, which resist oxidation and high-temperature creep. While these materials hold immense potential to withstand the rigors of ultra-supercritical environments, they also elevate construction costs, leading to sculptured trade-offs between budget and performance standards. As energy demands vary through the day, power plants must run at variable capacities, which introduces even further design complexities. The flexibility and adaptivity of turbine design are crucial. The new breed of advanced steam turbines, including the Siemens SGT 800, demonstrated efficiencies soaring above 40% even while accommodated for nightly load reductions. This adaptable design is attributed to additional engineering that allows for optimized operational efficiency across different loads rather than focusing solely on the highest possible output during peak demand times. While the stations can generate impressive quantities of electricity, estimated at around approximately 700,000 megawatt-hours per year, it is still vital for engineers to build a cushion within operation thresholds. By doing so, they not only institute longevity for the machinery but further contribute to a more sustainable infrastructure, reducing emissions and the wear and tear impacts inherently tied to higher operational outputs. Analyses show that with rising global temperatures and changing environmental standards, the energy sector must increasingly focus on creating operations that have a minimal ecological footprint. Engineers explore sustainable practices that not only meet energy needs but also mitigate environmental impacts, leading to increased attention toward integrated clean coal technologies. These technologies include innovative methods like carbon capture and storage, which hold the potential to bring down emissions considerably. Plants adopting these strategies still recognize the challenges of running equipment under sustainable limits, thus, they also focus on making adjustments to boiler design to enhance their efficiency without compromising safety. In fact, the current understanding of materials in high-pressure environments has directed researchers toward promising directions. From looking into composites that mimic the structural benefits of steel while weighing significantly less, to pioneering ceramics that function at staggering temperatures, the world of coal-powered energy generation continuously evolves through these investigations. Let us also not overlook the connection between output limitations and economics. Power plants must also navigate the cost versus performance equation. Every design decision revolves around the calculations of how much energy can be gained without incurring the potential hazards from fatigue and damage. The operational management of a plant like Ninghai is as much about governing human expectations and world demands for energy as it is about the raw capability of the machines. Take into consideration the global context. In regions where reliance on coal-fired power remains significant, the optimization of existing plants is critical. Nations are investing billions into retrofitting their plants with these advanced features, recognizing they can dance the line between pushing for maximum output versus creating a failure-prone environment. The longevity of equipment influences budgeting for energy policies and long-term planning for energy needs. This may seem contradictory when viewed through the lens of how competition encapsulates the energy sector. The drive for more energy output is always at odds with calculations about risks and longevity. Consequently, acquisition and operating expenses dictate that plants, when managed correctly, reap long-term benefits from sustained, predictable outputs. Thus, the average lifespan of efficient operations for an ultra-supercritical coal power plant under these principles can range from 25 to 30 years, contingent on proper maintenance and thoughtful operational strategy. At last, we have journeyed through an exploration of ultra-supercritical coal power plants and the unseen limitations they embrace. It has become clear that each giant machine embodies not only cutting-edge engineering but also a heartfelt commitment to safety, efficiency, and sustainability. As we peel back the layers of these complex systems, we come to understand that their functionalities are grounded in fundamental principles that extend beyond mere power generation. Just as a balanced act requires finesse and insight, so too do the giant coal power plants fulfill their purpose, threading the needles of social demands, economic viability, and environmental safeguarding. The careful reasoning and deliberate design choices present engineers must navigate propel these modern marvels. The machines